Hey, hi everyone. First of all, I hope everyone is doing well and is hooked on to the content on product managed. Uh, just wanted to share some news with you. The channel has crossed 150 plus subscribers. So thanks to all of you who have really liked the content. I definitely cannot thank you enough for the love that you have shown. So please leave comments if I have missed out on any concept that you feel is important. Today's concept coverage is more on topic related to system design interviews. It'll probably be asked more like let's say in one of the DSA rounds if you're doing software engineering interviews. On the product management side, yes, the concept is important, primarily because these discussions on hashing obviously come up, and this is one of the ways in which you can actually show that you have subject matter expertise to deal with the engineers who speak the same language, right? So without getting delayed further, let's jump into consistent hashing, right? So what is consistent hashing, right? So consistent hashing basically is a technique that is used in distributed hash tables, and it basically ensures that the same key, right, is always mapped to the same node. In reality, I think I'll show you later that there's a range of, I think, nodes to which the keys can be mapped. And what that allows is that when there are changes to your, let's say, network wherein the mapping is mapped, such as nodes joining or leaving the network, consistent hashing allows, to still, it still allows you to have the mapping in place, whether the nodes are coming or leaving the network, right? So, what is a method or methodology behind consistent hashing? So, basically, a hash function is used that maps each key to a point on a circle. I mean, this circle is basically imaginary circle, and then each mapping basically takes key as an input, and then you have an outcome as a node, and in between is your hash function, right? So you do get a range of points on the circle to which a particular key can be basically mapped, right? So this is what it is saying. A key is inserted into a distributed hash table. It is hashed to determine which node it should be stored to, right? When a node joins or leaves, that this is critical. When it joins or leaves the network, only the keys that fall within a range needed to be remapped to a different node, right? And what this helps is that it ensures that the same key, right, is always stored in the same node, even if the other nodes are basically changing, right? So before we get into that, I am just going to do a quick recap of what do you mean even by hash or hashing functions, right? So imagine like you have a database storage wherein you have all the, let's say, user keys, right? User one, two, three, and you are looking at an order table, right? That's also storing, let's say, data in some database, and where you have a mapping of the order IDs and the order name, right? And a hash function is basically used, right, to tell me that, for example, this user one, uh, let's say, is requested a item, right? I mean, that item could be anything out of this four, but the hash function is basically helping you map to that particular item, right? So a simple hash function can tell you that, for example, user one, basically a key, right? I mean, this is a key because it's a unique identifier for that user. Uh, that user one is basically going to look at uh, uh, order ID from this table, right? So let's say, for example, user one, when we pass the hash function, it goes to zero, right? It's assigned to zero, and then that's how the order ID is mapped, and you get whatever the order that you have, right? And then user four, let's say the outcome is that it is mapped to 1008 order ID, right? So notice these two numbers, 0 and 2. These are your hash outcomes, right, of the hash function that are allowing you to map this user to this particular table, right? And this hash is the basically a predefined, let's say, a set of random numbers that you could always choose. And then the hash function is basically allowing you to map to those, right? Now, why should I even care about all of this, right? And basically, does it even make sense to invest in such kind of uh, creation of a function, right? The part where I think hash functions have their efficiency is they allow you on super, like I would say, efficient storage and retrieval of data. So this obviously is a case of a SQL database, but you could pretty much argue it for a NoSQL database as well. And in an ideal scenario, the above mapping once fixed will work, right? But that is not how the the real systems work, right? In a distributed environment, what will happen is that you are going to scale up or scale down depending on your infra requirements, which could lead to a possible scenario, right? So now imagine like what is happening. And distributed environments are basically where I think, there's a functionality where you can obviously decide whether you want to bring in some additional nodes when you are scaling up your clusters, or remove some nodes when you are scaling down your cluster, right? So in this case, what will happen is that you will require resources to remap the earlier mapping orders, right? So what I mean by that is that if you look at this, user one was mapped to a zero hash, which resulted in mapping it to a 1001 order ID. Now imagine if you are scaling up or scaling down. Now what will happen is user one, uh, and when you scale up, obviously this mapping will still be like taken care of. You don't have to worry about this part, that when I'm scaling up, what will happen to zero? Zero is basically the hash table, way of identifying where is that particular, let's say, order, like that I'm looking for is mapped. What you will notice, I think, after the scale up, or let's say the scale down operation, is that the order ID initially that was mapped to, let's say, hash outcome 2, now is mapped to hash outcome 1. It is still the same order ID that is telling you this is the order, but the hash function obviously will now have to be considerate, that 1 is what 1008 is corresponding to, right? So if my user 3 is still looking for the original order, which was chocolates, right, I have to now go and look at hash outcome 3. So this is basically doing a remap of this column, basically, right? 0, 1, 2, 3 to this order ID, which is a lot of overload, right? I'm just showing you a sample of 4 orders. Imagine you have millions of, obviously, in a real distributed environment, you'll have millions and billions of orders, right? Like that. So imagine how much processing power you're going to waste just to do a remap, right? So that's not the most ideal way, right? So this is where the problem is. I hope you've understood the problem. If not, uh, go back and read about, I think, hash functions. So hash functions are, I would say, an encrypted manner in which any given input uh, through, let's say, a function is given a defined output. That output is always in the range. Like you'll have a range of outputs through which you're doing the mapping. So that is what a simple hashing, let's say, is. Now, what is consistent hashing, and how is consistent hashing going to be helpful, and how is it that going to solve the problem, right? So now we jump into this part where, let's say, each node has a set of users mapped to it, right? Let's say node 1 is mapping user 1, node 2 is mapping user 2 and 3, node 3 is mapping user 4, 4 is mapping 5 and 6, correct? Now, you would argue that, okay, also to set up more context, let's say user 2 and 3 are coming from a mobile app, right? And user 1 is coming from a web app, right? And there's a bunch of range of IP addresses, right, that you can obviously code and say that if my machines, right, or my app is belonging to that particular range of IP address, I'm going to map that to node 1, correct? Node 2, node 3, node 4, you can build out the logic, right? I mean, engineers can build out that logic. Now, what is the problem? It's obviously easy to add in this manner. Let's say easy to add a new node, right? Let's say I bring in a new node because I'm scaling up my infra. I want more users to be like, more users to have the being served the orders, right? So I bring in a new node. I map whatever additional users are there to this. Now, what happens? A node breaks down. very practical scenario. For whatever reason, I think until the node, let's say two, is backed up and the backup is up and running. What is it? And even though you might have backup, you can always, like, I think you can very well argue that for each node I can create a backup, right? But that's not, I think, efficient replication strategy for databases. You can obviously create backups for all your infra, but that is not how in reality the cost will support your argument in front of the leadership, right? So I think node 2 breaking down is going to create a problem here. What is going to happen is that this guy here, right, user 2 and 3, will be left without any mapping here. So now how do you decide which node this user 2 and 3 should be mapped to? So decision to route to node 1 or node 3, basically those are the only two nearest nodes, right? Would should be ideally, like, you can be consistent in the logic. You can always say that I'm going to map it to the nearest lowest node, right? The next lowest node, while going in a circular fashion. So here, for example, if I remove node 2, which is this guy is gone, I'm left with user 2 and 3. Right now, 1 and 3, obviously 1 is the lowest, between, like, 1 is lower than 3, so you basically do that, right? And then this node, until node 2 comes up, is now ready to take the load of these users as well, correct? So this is how I think scaling up, which is like doing this part, node 5, and scaling down, which is this part, helps. Now, I think one question that could come is that when you added a new node, why didn't you add it to, let's say, node 4, right? Because I think for node 4, there's already the whole concept of adding a new node is that I'm able to map a new range of users, right, to a particular new set of node, right? So it doesn't make sense to basically route it to the same node that is there. In case this node goes down, where is it that you are going to map it? Again, if node 5 goes down, then your user 7, 8, 9 are left in a limbo. There is no way that they are being served by this node because node 5 is down, right? So your immediate choice, going in a circular fashion, always remember that you're going in a circular fashion. Node 1 is the option, correct? And let's say I'm deciding between the nearest nodes, right? Node 1 is the option. I go back around the circle, I get node 4, right? Which one is the nearest? Node 1 is the nearest, right? So I'll assign 7, 8, 9 to user, 7, 8, 9 users to node 1, and then user 1 is already there, right? So that's how you will, tackle that. I hope, I think this gave you a fair bit of idea of how easy it is using consistent hashing to scale up and scale down, correct? Now coming to some of the practical usages of consistent hashing, and like, I'm going to cover mostly real, like, I think, applications that are using consistent hashing. Right? So distributed databases, basically such as Apache, Cassandra, React, DynamoDB, these all have the option of using consistent hashing. Uh, Obviously, as I mentioned, right, consistent hashing is going to help you in data retrieval, correct? And it's also going to ensure that data is always stored on the same node, right? Even in the event of node failure. So what it means is that obviously your logic will tell you that once this node 2 is down, you are mapping it to the nearest lowest this thing, right? And what it means by the same node is I, for example, could always create a node 1 ka copy and call it like whatever node 2, right? And then I can map it. That is what it means here. Allows for efficient data retrieval and ensure that data is always stored on the same node, even in the event of node failures or changes in the network, right? So cloud providers can basically, cloud providers can give you that flexibility where you can say that in case a node goes down, what should my system resort to? Do I create a backup of that node and bring it up, which will incur a cost? Or if I am not using that, what is my next best option? Then you can always say that I'm going to map it to the lowest, nearest lowest numbered node, right? In that case, it will do this, what we just discussed, right? So Amazon's DynamoDB, right, use consistent hashing, and it is used to distribute data across multiple nodes. There is a technique that they is used. It's called Vladimir's variant. I don't have a lot of idea about this. Feel free to Google it and read about it. But I think one of the obviously functionality of this hashing algorithm would be the underlying way or the underlying manner in which you are actually deciding once the node goes down or once the node is brought up, how is the mapping going to be done? Correct? That is the fundamental behind any algorithm in any of the distributed database. Cassandra is using, obviously the same, but a different, let's say, murmur tree, to handle failures and change in the network. React is another one, uses React's conflict, tree replica data type, CRDT. Uh, Whether you will be expected, yeah, I mean, if you're looking at software engineering interviews, a pretty straightforward question could be that our infra is on Apache, Cassandra. So, what algorithm do you think is implemented? Murmur 3, I think, you could look at. But generally, I think no one is going to expect you to write down a Vladimir variant and Murmur 3. I have not seen that happening. So, this is more for your knowledge. And you also sound very good when you talk about this. Shows that you have the depth, right, of the subject. And Google's Big Table, right? I mean, that is again a distributed column oriented NoSQL database service, right? It uses a variant, obviously, of consistent hashing. Combination of, I think, algorithms, and then helps you with deciding what to do in case of node failure or sizing up the node. Another area where consistent hashing is commonly used is the P2P networks, such as BitTorrent and Cadmilia. Um, this is, I mean, okay, obviously the data is distributed across multiple peers, right? The peer becomes your node, and you allow for efficient data transfer, and you are looking at same data being retrieved from the same peer. So what happens if the peer is down? You move on to the next whatever peer, right? Maybe the peer has the copy of the data, right? Obviously, I think this is helping you reduce the latency and improving the performance. Correct. So that is what peer-to-peer network application is. One algorithm that is used is the chord algorithm, and it's a distributed hash table, as we had discussed. Correct. Right. So for peer-to-peer network, chord algorithm. For distributed database, couple of algorithms like Vladimir, Murmur 3. Right. So just remember that. Now, OpenStack Swift, correct, is basically an object storage system. Again, based on the use of consistent hashing, and it is used to distribute data across multiple nodes. So this is more like a data distribution, use case, correct? Um, it is using some sort of consistent hashing, but they have their own because it's an open source, open stack, storage system. There's a variation to the consistent hashing algorithm. I am not sure of the details, but I'm pretty sure that if you are interested, I mean, leave a comment. You want me to cover it, I can cover it, but it should be available, I think, to be discussed detailed further. CDNs, right? I mean, CDNs, content delivery networks, is where all your static data is stored, right? Like your images, your, let's say, videos, right? And across obviously multiple servers, you can use that, right? The same content is always served from the same server, correct? Reducing latency and improving performance. So most of the use cases that you are seeing right here is actually helping your systems to be more easily available, right? The content has to be more available, the data has to be more easily available, right? Leading up to, let's say, the 99.9959 or 6 nines, kind of perform availability, correct? Load balancing, without a doubt, can be used, one another application. You can, if you look at it, right, this chart, if I have a bunch of applications requesting data, right, then I can very well define the function and then distribute the data to different nodes, correct? So in this case, your nodes become your server. So this will be server 1, server 2, 3, 4, 5, right? And that's how you can ensure that no single server is ever overwhelmed with majority of the requests. File systems, again, distributed file systems, it says Hadoop, right? consistent hashing is used here to distribute files across multiple nodes. This I have used practically, and I have used it uh, in various, I think, capacities when I was a machine learning engineer, and also as a product manager for a startup. The use cases there were basically focusing on efficient file retrieval, because we were storing a lot of, I think, customers' structured and unstructured data. But our use case was to ensure that retrieval, is done without failure. So this is definitely a real use cases, that you see on file systems. Also, I think file systems, for example, if you recollect, when we had discussed about Google Drive, correct? You remember, I think, let me take you back, right? So on Google Drive, on the folders with file side, right? This is where we had discussed the NoSQL component, right? So in such a case, for example, you can always argue that I will build this on a, let's say, a distributed file system, right? Such as a Hadoop, system. So this is a direct link to that concept here, correct? Cloud computing, obviously, said Amazon Web Service Azure use to distribute data and applications across multiple servers for any of their services. When you're using storage, compute, machine learning services, I think instead of putting load on one server, you can just use consistent hashing, direct them to, multiple different servers. Social networks, yeah, Facebook, LinkedIn, data, again, distribution of data is what it is looking at across multiple servers, correct? And data is always stored, obviously on same server. By same server here, it means that node 1 is one server, so I can always have a copy of node 1. And the logic could be that once node 1 is down, I bring up that copy, which still means that user 1, let's say in this case, will not be affected, right? So consistent hashing is always use case will be like ensuring that you have availability of data, very high availability of data, right? And the last use case around cryptocurrencies, Bitcoin, Ethereum, they're using transactions, right? So blockchain transactions, if you are aware of, right, that's how validations are done on a blockchain. They use that also, that algorithm, to ensure that multiple nodes on the network are available, correct? Always stored on the same node, correct, and reduces the risk of fraudulent transactions. So I think this video gave you a great sense of what is consistent hashing, what is also in fact hashing, right? We covered that in the first part. And so do leave out comments, and until next time, I hope you have leveled up your learnings by significant notches. And uh, if you are looking for product management mock interviews, there is a link on my channel. You can block the time using the top mate link. I am usually available, and through that, I'll get the notification. I am also planning to do an AMA session, which is Ask Me Anything session. So stay tuned for that. And until next time, take care.